All right, today we're diving into a really deep problem in geometry. The paper's title is, well, it's a bit of a workout: Conformal Twists and Geometric Pseudofunctoriality of Positive-Chiral Spinorial Complexes on Compact Kähler Spin Manifolds. But don't worry, behind that huge mouthful is an idea that's actually incredibly elegant and powerful. So, let's break it all down.
So what we're looking at here is a brand new paper from Mohammed Ben Ammar Charaiti, who is an independent researcher from Tunisia. This is a recent preprint, so it is absolutely hot off the press. And this work is really the latest step in developing a super powerful set of tools for geometers, something known as the FUCG framework.
So what's the big mystery we're trying to solve today? You know, it all boils down to a question that sounds pretty simple but has some really complex answers. What happens when our mathematical maps, the ones we draw between geometric shapes, don't quite line up perfectly? What happens when the translation from one shape to another isn't clean, but instead introduces some kind of twist or distortion?
Here's the game plan for how we'll walk through this idea. First, we're going to introduce the special map that's used for these complex shapes. Then, we'll get right into the twisting problem that it creates. After that, we'll see the big breakthrough moment that cancels out all the chaos, and then we'll see how a new geometric language is built from that solution. We'll look at the incredible payoff, and finally, we'll explore where this research could go next.
Okay, first up, the map for complex shapes and what's called the FUCG framework. This is really the foundation for everything else we're going to talk about.
Probably the best way to get your head around the FUCG framework is to think of it as a system for giving every complex geometric shape a unique mathematical fingerprint. We're talking about things called Kähler spin manifolds here. This fingerprint, which is technically called a spinorial complex, it captures the shape's most essential properties. And that allows mathematicians to study them, to compare them, to really understand them.
But, this mapping tool, it isn't quite perfect. And that brings us right to section 2, the twisting problem. This is where the central conflict of our story really starts to heat up.
In a perfect world, mapping from one shape to another would be just a clean, direct translation of its fingerprint. Easy, right? But reality, it's a lot messier. Previous research found that the map itself actually introduces a twist. So the fingerprint of shape A doesn't just arrive cleanly, it gets warped, it gets distorted on its way to becoming the fingerprint for shape B.
So you might be thinking, is this twist just random chaos? Well, not at all. It's actually governed by a super precise mathematical rule called the ramification compatibility condition, or the RCC. And this is key. It's not a bug in the system, it's a fundamental feature of how these geometric maps work. The RCC tells you exactly how and why the twist happens, which turns it from just a problem into a phenomenon that we can actually study.
Which brings us to the climax of our story in section 3, canceling the chaos. This right here is the core breakthrough of the entire paper.
So this twist we've been talking about, it doesn't just make things complicated on paper, it introduces a real mathematical mess. Along the parts of the map where the geometry gets tricky, that's called the ramification divisor. Two specific terms in the equations just blow up. They create these infinite values known as logarithmic singularities. It's kind of like trying to draw a map that has actual rips and holes in it.
And this is where we get that incredible aha moment of the paper. The author proves that these two messy, singular terms aren't just there by accident. In fact, they are precise opposites. They cancel each other out, perfectly, point for point. All the infinities just vanish, resolving the chaos and revealing this hidden, perfectly smooth mathematical structure underneath. I mean, it is just an incredibly elegant solution.
Okay, so with this cancellation understood, the chaos is finally tamed. And this allows us to move on to section 4 and actually build a new, much more powerful geometric language. The author uses this new stability to build a whole new mathematical framework from the ground up. It starts with the basic objects, which are designed to handle these twists. Then it defines the pathways between them, called one-morphisms. And here's where it gets really cool. It even defines relationships between those pathways, which are called two-morphisms. When you put it all together, you get this rich, multi-layered structure called a bicategory.
So the crucial point here is that this isn't just patching a problem. It's like going from having a simple list of words to creating an entire grammar book. This new bicategory and the mapping tool that's built from it, a pseudofunctor, they give us a rich, coherent language to describe not just the shapes themselves, but the really complex, twisted relationships between them. So what's the payoff for all this work? Let's take a second to sum up what we've actually gained with this new, coherent framework.
This paper really delivers on 4 key achievements. First, we get a rigorous, solid way to handle these twisted maps. Second, we get a deep understanding of why the twist happens by identifying its exact mathematical signature. Third, we have a coherent framework to organize this whole phenomenon. And finally, it even shows us the very, very rare conditions under which a simple, untwisted world might actually be possible.
Now, like all great research, this work answers a lot of questions, but it also opens up some really exciting new ones. So let's take a quick look at the future of this FUCG framework.
The paper wraps up by teeing up several new questions. For instance, does this twist connect to even deeper mathematical structures? Can we build even more powerful tools to describe it? And how does this new model relate to other advanced areas of geometry and algebra? This work clearly isn't an ending, but a whole new beginning.
Ultimately, what this explainer shows us is the power of finding just the right perspective. What looked like a chaotic bug, when you view it through the right lens, became an elegant, predictable feature. And it really makes you wonder, what other seemingly messy problems, in science, in math, or even in our daily lives, aren't problems at all, but are just waiting for us to invent the right language to understand them?